Okay, last lecture we have developed power series for sine function, and in developing that series what we were required was the derivatives. First derivative, second derivative, dot dot dot, nth derivative, and sine x was very good function when we got f of x is equal to sine x, where we got whatever derivative we want, nth derivative was available, and therefore we evaluated system series for sine x and we wrote it down. We were not, I mean, that is what is the first step towards finding out what is the series for sine x, and we ended up getting x minus x cube upon 3 factorial plus x raised to 5 upon 5 factorial minus x raised to 7 upon 7 factorial and so on. And what was our formula? F of x was equal to f of 0, don't differentiate, I mean the function itself, to be evaluated at c upon 0 factorial into x minus c raised to 0 plus first derivative evaluated at c upon 1 factorial x minus c raised to 1. Every time it is going to give it. Plus second derivative evaluated at c upon 2 factorial into x minus c raised to 2 and so on. Okay. In case of sine x, we considered base point equal to x is equal to c. Okay. So before we really figure out and give legal status to this particular expansion series that we have got for sine x, let us try to figure out what should be the
Sir,
series expansion for cos x. Oh,
sir, base point upon x equal to 0 घेतलेलं ना?
in this formula base point is c. In sin x base point is 0. Find out expansion series of f of x is equal to cos x, considering base point x is equal to 0. Correct. So exactly similar way, the way we have done it for sin x, we can do it for cos x, because cos x also after fifth derivative it will repeat and you can express it in terms of pi by 2, and then you will get, once you do all that calculation, you get series expansion of cos x as something like this. Next easy function of which you should find out series expansion is e raised to x, because derivatives are easy. Yeah. So e raised to x looks like 1 plus x upon 1 factorial plus x square upon 2 factorial plus something like this. Okay. Now sketch y is equal to x square. Then y is equal to x square by 2. Then y is equal to minus x square by 2. Then y is equal to minus x square by 2 plus 1. दाखवा मला हे चारही प्रोग्रेशन्स करून स्केच काढून. First y is equal to x square, then second graph y is equal to x square by 2 approximate. Okay, the four graphs will look like this. Y is equal to x square, standard upward opening parabola, half flat parabola, minus half coefficient makes it upside down, and we'll pan it up by 1. What I am trying to do is I am just stopping at this point. Cos x is equal to 1 minus x square by 2. So 1 minus x square by 2 will look like this, and if you really sketch cos x in the neighborhood of 0 base point, the graphs will coincide. That is the whole idea. If you try to sketch x raised to 4 by 24 minus x square by 2 plus 1 as f of x, which eventually is approximately equal to cos x, you will have better fit, better comparison of actual cos x graph and this polynomial graph. That is what I wanted to bring it to your notice. We did it in case of sin x also. First two terms, it's a cubic, and I add 0. X minus x cube upon 6 behaves like sin x. I am demonstrating that at 0, near the neighborhood of 0, in the neighborhood of 0, the behavior of this polynomial x square by 2, negative x square by 2 plus 1, and behavior of cos x is similar. That is what is the idea of asking you to sketch the curves. It will be similar for e raised to x also. You can try it later, but give me some more series expansions. Find series expansion of f of x is equal to a raised to x. A raised to x, you can do it using e raised to x. E raised to log, e raised to log a raised to x. I see it is equal to a raised to x, and you know e raised to x. So e raised to x log a is equal to a raised to x. So now you can consider this as your t or something like that and write down the same series expansion. Constant times x. So e raised to kx f of x is equal to e raised to kx will look like 1 plus kx by 1 factorial plus kx raised to 2 by 2 factorial plus kx raised to 3 by 3 factorial and so on. So e raised to x will behave like this, and k in this case k is log a. That is the only difference. Log a is a k here. Okay, so what is series expansion of e raised to ix? Suppose we are allowed to use this imaginary number as a coefficient of x. Can you write down series expansion of e raised to ix, where I is a root of unity, square root of unity. In this case, k is equal to I, right? Therefore, we start writing 1 plus ix by 2 by 1 plus I square. I square, that is minus actually. So let me save one step. I square x square by 2, which is minus x square by 2 factorial. Then I square I x cube by 3 factorial. So minus I x cube by 3 factorial plus, that is I x raised to 4. I raised to 4 is 1. So it is x raised to 4 by 4 factorial plus I times x raised to 5 by 5 factorial minus x raised to 6 upon 6 factorial minus I x raised to 7 upon 7 factorial. So 2 plus 2 minus. Now if we really look at it, and if I wish to write it like this, e raised to I theta, then it will be 1 plus I theta by 1 factorial minus theta square by 2 factorial minus I theta cube by 3 factorial plus theta raised to 4 by 4 factorial plus I theta raised to 5 upon 5 factorial minus theta raised to 6 upon 6 factorial minus I theta raised to 7 upon 7. And now if I really combine the real and imaginary part, 1 minus theta square by 2 plus theta raised to 4 by 4 minus theta raised to 6 by 6 factorial plus dot dot dot. This is going to be your real part plus I times imaginary part is theta upon 1 factorial minus theta cube upon 3 factorial plus theta raised to 5. 5 factorial plus minus theta raised to 7 upon 7 factorial plus dot dot dot. This is your imaginary part. And surprisingly, what we end up getting here is e raised to I theta is equal to cos theta plus I sin theta. That is our cis. So this completes the story of our complex number notation, that it has also, we have learned all notations of z, x comma y, then r comma theta, then x plus iy, then we cis theta. Many notations we have learned at that time, and we also said that it is e raised to I theta. Of course, the magnitude is r here, and because magnitude r is 1 here, we are getting it is equal to cis theta. So this completes that story. Why complex number is to be denoted by r e raised to I theta? Maybe one way of looking at it. I am not saying that this is proof, but one way of looking at it is the series expansion. Because right now, why I am not considering this as a proof, because I am studying real analysis, and my series expansion theory, which I am trying to develop, is for real numbers, is true for real numbers. And suddenly I introduced I over here, which is a complex number. And however, I am getting exactly the thing that I wanted. That makes it very interesting. That is good enough for us to understand why e raised to I theta behaves like cis theta. It is because of this. It is because of this, and it is amazing. It is surprising. And you need to enjoy it. Okay? So note it down before we proceed. It is important that you figure out what should be the series expansion of a given function, so that it helps you to remember that. Next function is log 1 plus x. Find the series expansion of log 1 plus x. Okay, so for any function, if you can write down the successive derivatives, nth derivative easily, then at least writing the series expansion is easy because we have what the correct formula with us. How to write down polynomial function or a series power series expansion for a given function in terms of higher order derivatives. So if the differentiation is easy, it has got some pattern, then it is easy to write down the series expansion, right? So in this case also there is a pattern by which we can write down the series expansion, correct? Let me just write it down. What is the correct answer, and then we move. So log 1 plus x, if evaluated at c is equal to 0, then it is x minus x square by 2 plus x cube by 3 minus x fourth by 4. They are not factorial because something gets cancelled in the numerator, plus x fifth by 5 minus dot dot dot. Okay. uh, I mean, we will have to discuss this function and figure out what are the restrictions on it, what are the conditions on it, so that it is true or is it true for any x, etc. We will discuss that. Now, let me give you an easy function, 1 plus x raised to alpha, where alpha belongs to a real number. Okay, so what will be the series expansion of 1 plus x raised to alpha? Find out. So if alpha is a real number, then your series expansion looks like something where if alpha becomes natural number, then it is a binomial expansion. It is as good as that, which is equal to 1 plus n upon 1 factorial times x plus n into n minus, सॉरी n म्हणजे माझ्या नोट्स मध्ये n आहे, तुम्हाला मी अल्फा दिलाय, अल्फा minus 1 upon 2 factorial x square plus alpha into alpha minus 1 into alpha minus 2 upon 3 factorial into x cube. So how many brackets? जेवढा factorial असेल तेवढे brackets. So it's a 3 factorial, therefore there are 3 terms in the numerator, x cube, right? And so on. So this is what we had assumed, that if the index is a real number, then during generating functions, when we learn generating functions in combinatorics, we have assumed this alpha as a real number and it will work all right as far as expansion of 1 plus x bracket raised to alpha is concerned. We said it will work all right, and at that time it was assumption. Now it is little better than that. We have not proved it yet, but it is better than that. Our series expansion method is giving us the exactly same. Now, if we replace alpha by natural number, it is a binomial expansion. So it takes care. So binomial expansion becomes a special case of this. That is what we can say at this stage. So this series expansion is really a major breakthrough as far as calculus is concerned, and it has got several applications. Actually, the majority of the applications got opened because of this change in concept. Okay, is there anything which is still remaining which I can ask you to expand? Okay, little difficult, but just try, because you are doing it anyway right now since morning. You try this. F of x is equal to tan inverse x. Can you get successive differentiations and generalization of derivatives, or at least write down first 4 terms? Right, first 4 terms of expansion. Tan inverse x. Okay, as far as tan inverse x is concerned, if you do the derivatives, you will eventually get a series expansion like x minus x cubed by 3 plus x raised to 5 by 5 minus x raised to 7 by 7 plus standard. Okay. Okay, good enough. Now, using this formula that f of r to be evaluated at c, f of r to be evaluated at c upon r factorial into x minus c bracket raised to r, sigma r is greater than or equal to 0. We get the series expansion of f of x. We have done this. We did it for polynomial, it worked. And we did it for sine, it seems to be working, cos, and then whenever nth derivative of a function was possible to evaluate easily, this function we can write as series expansion. Now, but is it correct? Is it correct to write the equality sign? Equality means a lot. Equality means LHS is exactly equal to RHS. We cannot afford to have any difference between the two quantities. And then when we are saying that it is exactly equal, and we end up putting some dots after this, and we are not writing all the terms, we are saying that there are infinitely many terms, then it is a big responsibility on us to figure out equality. Whenever you are writing equality, it is a very, very important step. Saying it is approximately equal to, then maybe it is okay. But when we are saying that it is equal to, or we are going to do our calculations based on equality, we might be in trouble unless we deeper and write down the proofs and figure out whether every step is correct or not, whether it is true for all or not, or is it true for only few series expansions, etc. Okay, so we begin our discussion on that now. Now, if we simply take a series, which is say, for example, e raised to x, let us take e raised to x, series e raised to x. 1 plus x by 1 factorial plus x square by 2 factorial plus x cubed by 3 factorial plus x fourth by 4 factorial, etc. plus that. We will have to figure out, are we eligible to write this sign equality between these two terms? So as a layman, what will I think? And moreover, what we are trying to say is this is series expansion, and as you take more number of terms, you will be better, because e raised to x near in the vicinity of x, which is equal to 0, the graph is like this, e raised to x, graph is like this, and this is x is equal to 0. So if you take only first term, the function is approximated by straight line, which is y is equal to 1. But if you take first two terms, this plus 45 degree here, you add these two quantities, and maybe you will get something like this, because you are adding constant number to that. And then what we are saying is, if it is a two term, then it is this straight line, you refer to this straight line. If it is only one term, you refer to this straight line. And the second straight line is little better approximation of the curve near 0. However, if we do it quadratic, maybe we will end up getting something like this. And then you say, okay, this is better than straight line, because if you really zoom at 0, it is a better approximation there. And so on. We are saying that if you add one more, if you add one more, if you add one more, you will be better off as far as value of the function near base point is concerned. So is it, so therefore, when should I stop? Suppose I stop at x raised to 4 upon 4 factorial, am I eligible to write equal to question mark? Or still, if I stop at x raised to 100 upon 100 factorial, am I eligible to write equality, or still it is not equal? That is the ambiguity that we have to sort out. Another function which we can consider along with e raised to x may be what we have already done, log of 1 plus x, and its series expansion is x minus x square by 2 plus x cube by 3 minus x raised to 4 by 4 plus x raised to 5 by 5. Now here again you understand that you are adding more number of terms whose powers are also growing. X raised to 5 by 5 is a huge number if x is greater than 1 or less than minus 1. It is very less if it is negative, but if x is greater than 1, then adding x raised to upon 5 is a big quantity that you are adding. So one stage we say that if you take more number of terms, you are better off. Maybe in this case, if value of x is bigger, you take more number of terms, you are not going to be better off. I mean, you will make the function bad by adding few more number of terms. Do you understand this? If it is x, then log 1 plus x is equal to x, or log 1 plus x is equal to x minus x square by 2. So we are trying to do some correction here, because when we say it is equal to x, it is on higher side value RHS. So we subtract something, some quantity. Then suddenly we realize that we have got into negative side, therefore we add some quantity. Something like this is happening here. So if you were given a responsibility of finding out how do we ensure equality, how do we say that yes, this is the correct series expansion of a given function, then how will you go about it? तुमचं सजेशन काय आहे? कारण see finding higher order derivatives is a difficult task. But suppose I assign somebody that okay, I have 40 students in my class, tan inverse x, first derivative somebody will find out. After he finds out first derivative, I assign it to second student, he will find out second derivative. After he finds second derivative, I will assign it to third. So I can get 40 derivatives. It could be a labor work, lot of labor work. Fair enough, but I can find out. But then after finding out all the derivatives, if I write the series expansion of that function, just because we have proved it for polynomials and it seems to be working there, shall we say that it will work for every function? Or shall we sort out some functions for whom it will work and for whom it will not work? Or by and large it will work to all. That means we have to be a little careful in choosing those functions, taking their derivatives and evaluating the function near base point and saying confidently that yes, you can write equal to, provided. That provided thing, can you think and tell me what should be the necessary and sufficient conditions to which we can confidently say that equality will exist? We can actually write the equality sign over there and do something about that series expansion so that I am confident that near the base point the function will behave like this, and the series expansion of the function will also behave exactly like this. What is that thing that we need to be sure about? जरा विचार करा आणि मला उत्तर द्या. Maybe write down and show me your thinking. These are the questions that we need to answer. When and how and why should we have this equality sign? Okay, and for that it is very simple. The idea is very simple. Now, if, as I said, if in case of e raised to x function, in case of e raised to x function, in the vicinity of x, that means x is equal to 0, base point 0, in the neighborhood of base point 0, if I start putting different values in this series expansion, I will get better and better. We can observe that we can actually put these values and check, we can sketch them and observe that we will, the more number of terms that we add, the value of the function becomes better and better. That is what we will get in case of e raised to x. But in case of log 1 plus x, if we say that my 1.1 is also near 0, 1.1 x is equal to 1.1 is also near 0. Suppose, because nearness, that way you are not defining. So you can say compared to 5000, 1.1 is very near to 0. So my 1.1 value of x, if I put, then you will observe in this series expansion that as you take more number of terms for say x is equal to 1.1, what you are going to get is, if you stop at only first term, you will get value 1.1. 1.1 at first term, 1.1. If you subtract second term, 1.1 raised to 2 upon 2 will make it very less subtracted. And if you take third term, you will add 1.1 raised to 3 upon 3. It will become more than the first. When you subtract fourth, it will become worse. I mean, like this. Fifth, it will become like this. Sixth, maybe it will go to negative side. Seventh, eighth. So my value of the function is here. When I put 1, I get this. When I put second term, I get this. Third, I get this. Fourth, I get this. Fifth, I get this. And so on. Suppose it happens like this. Then we are calling it as oscillating but divergent. Right? However, here you will find, if we put, say, value of the function near vicinity of x, then e raised to something value is here, then you put only 1, then you get, suppose you put 0.1 or something like that, 0, then it is 1, 0.1 will make it little less, then it will be little more, then it will be little less, then it will be little more, little less, little more, little less. So the bandwidth of the values, I mean, there is no negative sign, so it is going to be increasing only. So in case of e raised to x, the value is here. I can make a dotted line there. I want this value. If you take only first term, you are here. If you take second term, you are here. Third term, you are here. Fourth term, you are here. Like that, it will go on approach. So in case of e raised to x, as you take more number of terms, you will be better off. In case of log x, I mean, it is, the graph is going to be like this. In case of sin x, maybe if we look at the sin x function or cos x or a sin x function, then value of sin x will be something like this. The graph will be something like this. You want x is equal to, suppose 0 च्या vicinity मध्ये तुम्ही pi by 3, pi by 4 काहीतरी टाकला. So sine of pi by 3 is 1. The sine of pi by 3 is half. So this is your half. So pi by 3 is little more than half. So if you take only one term, you are here. Then you are subtracting little less quantity, but still you are not hitting this. This is your required value. If you take 2 terms, you go here. If you take 3 terms, you go here. If you take 4 terms, you go here. 5 terms, you go here. Just understand what I am trying to say. Now, this is what is the pattern for higher values of sin x. This is what is the pattern for lower values of sin x. And this gap is becoming less and less. Therefore, they are fluctuating, they are vibrating, but the vibrations are, the amplitude of the vibrations is becoming smaller and smaller. In case of sine and cos, behavior will be like this. In case of log 1 plus x, if x is here greater than 1, then the behavior is going to be like this. In case of e raised to x, it is smooth, going near to required value as you. So it is the difference between the RHS and LHS that need to be looked at. It is the difference between RHS and LHS that need to be looked at. If you stop, and you cannot say, for all practical purposes, you cannot say that it is a series expansion and you keep doing it. We will not be able to say that because we want answer. We cannot keep adding terms. They might not make any sense to us. Therefore, even if we are saying that they are power series expansions, we will add finite number of terms and find out what is the difference between LHS and RHS. And if we could compensate and calculate that difference in RHS and add some term over there, you add some quantity from your pocket and make it equal, then yes, equality sign can be applied. Lakshat gya. Now I am telling you very important thing. If the functions are good, well behaved, and if you are writing f of x is equal to series expansion, this series expansion sigma f rth derivative evaluated at c upon r factorial into x minus c raised to r. Now, as such, for all r greater than equal to 0, if you stop at r is equal to n, this is not going to be equal. It is going to be unequal. But then what I am trying to say is you add some x quantity in RHS or subtract some x quantity in RHS. Then you will be eligible to write down one. Okay. So this is what we will call remainder. If we could calculate the remainder term very successfully, what is the difference between them? We add that remainder in RHS and make them equal. That will reduce your error to 0 for all practical purposes. Then the next task is going to be, how do we find this remainder? How do we calculate the value which is the difference between the series expansions of n terms versus actual value of the function? How do we find out this? And what should be the value of the remainder that we should put? On what parameters it should depend, etc. We will have to work out. But the idea is you add some quantity and it is going to be very small quantity and you say that they are equal. If the function is fluctuating like this, then it is impossible to add this quantity. Because the moment you take next term, you are deviating from the original value with a great extent. You are adding unnecessarily a big quantity here. So if the behavior of the function is this remainder calculation is going to be impossible, we will not be able to figure it out, and hence answers are not going to be correct. This remainder calculations will be successful and will work provided what we call these functions eventually convergent, or what we can say in other words, if we evaluate the remainder r, because if I stop after 2 terms, I will get some remainder. If I stop after 3 terms, I will get some remainder. If I stop after 4 terms, I will get some remainder. And yes, if that value of remainder If you take more number of terms, will become smaller and smaller. Those series expansions are legally allowed. बघा लक्षात येते का? So what we should evaluate is, first of all, what should be the formula for that remainder, and different mathematicians have different formula for finding out remainders. We will learn one in detail and second one just without proof. We will find out what first remainder is done by Taylor, second remainder is done by Cauchy. So there are two different remainder calculations done for getting the equality of these two, function and its series expansion. Taylor's remainder we will try to find out and prove it, why it should be like that. And if after finding out the remainder term in RHS, if we observe that as R tends to infinity, the remainder term tends to 0, then yes, we are perfectly all right. You just add that pinch of quantity in RHS and say that RHS is actually equal to LHS. And your calculations will be correct. Everything will be in place. Everything will be all right. But if that remainder, whichever remainder that we are trying to find out, say for example, in case of log 1 plus x, that remainder we are finding out. That remainder, if it is divergent after taking the limit as n tends to infinity, as r tends to infinity, then that correction is never possible. Then you will not be able to say RHS is equal to LHS, because that remainder is dynamic and it is growing. You will not be able to correct it. You have to keep your problem under control. Then only you can write down that equality sign. बघा लक्षात येते का? So this is what is the thinking behind legalizing these expansions, writing the proof for the expansion. So we have to write the proof in terms of f of x. We cannot say we will write proof for sin x, we will write proof for cos x. We will have to say that whatever last lecture work which we have done, which worked for polynomial, if it is to work for any general f of x, then what must happen? Then remainder term should look like this, and remainder term should be convergent or tending to 0 as n tends to infinity. These are the two things that we will have to work on, and those are the theorems related to series expansion. समजतंय? कोणाला काही डाऊट आहे का? Okay, now see, this is whatever I said just now. You have to, in 5 sentences at least you need to make a note of it. Why should we have? Because directly I can write down the Taylor series expansion, that extended mean value theorem, and I can ask you to prove it. But then why should somebody think of that kind of theorem at this stage? That is what I was trying to explain you in the last 10 minutes. At least write a paragraph, whatever you have understood by this discussion, and why there is a need for doing that particular theorem in your language. Okay, so let us write down the theorem and its proof, so that whatever we have discussed just now is put in place. This is called Taylor's theorem. It is also called extended mean value theorem. Let f be a function from a to x y. If 1 f n minus 1 exists and is continuous on a to x to f n exists and is differentiable. Sorry, fn exists, that means it is differentiable on open interval a comma x, then 3. There exists a point C belonging to a comma x such that f of x is equal to f of a plus first derivative evaluated at a upon 1 factorial into x minus a bracket raised to 1 plus second derivative evaluated at a upon 2 factorial into x minus a raised to 2 plus dot 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 plus last term f n minus 1th derivative evaluated at a upon n minus 1 factorial x minus a raised to n minus 1. So these are the terms that we used to write. Now we have decided to stop at n minus 1, and then therefore there is a difference between LHS and RHS, and hence we add one more term which is f n at c. This c is different than this a upon n factorial into x minus a raised to n. This is what your remainder term is. Okay, so Taylor says that this is what is your remainder term, and if you use this term and if you take a limit as n tends to infinity of this term, and if it is convergent, if it is tending to 0, then yes, this series expansion is legal. And let me just highlight this equality. This is equal to and not approximately equal to. That is what is the meaning of this theorem. Now, I am aware that proving this theorem is independently, if you have not read the proof earlier, is difficult. But still, I would like to give you 10-15 minutes to think about how somebody could arrive at this particular term, number one, and maybe you need to think that it is extended mean value theorem. Okay, so that is good enough for you to spend 10 minutes of your thinking to figure out how the proof of this should go. And then I will give you a hint, give you sufficient time to prove it again. Okay. Okay, let us think of writing proof of this theorem. Note that the first few terms, n minus 1, 0 to n minus 1. So total first n terms are looking like polynomial only, except the last term which is remainder term. And this remainder term, the value of the difference that you are supposed to add is being evaluated here. So the difference between all earlier terms and last term is the nth derivative is not to be evaluated at a, but it is to be evaluated at some point between a to x, and that value will there will exist value of c. The theorem says that there will exist c, which is x is equal to c, which will give you this value, which if you add, LHS would become equal to RHS. Okay, so note, remainder term depends on? One, the function itself, f, because f, nth derivative of f is to be evaluated at c. So it depends on f and on second value of c, x is equal to c. It depends on these two quantities, which is fine. We want it to be dependent on the function and some point in the vicinity of a, in the neighborhood of a. So the neighborhood is ax is a neighborhood only. In the neighborhood of a is ax. X is a dynamic point, but you can bring it near a as much as you want. Okay. So proof. Define. Now every mean value theorem that we have proved earlier, we have defined some function, considered some function. So define g from closed interval a to x to r given by g of t is equal to f of t plus f1 to be evaluated at t upon 1 factorial into x minus t raised to 1 plus second derivative evaluated at t divided by 2 factorial into x minus t raised to 2 plus dot 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 plus f n minus 1th derivative evaluated at t divided by n minus 1 factorial into x minus t raised to n minus 1, and then the way we have assumed a into x minus t raised to n. Now we are supposed to find out this a, what this a should be, so that in fact so that we can apply Rolle's theorem. Rolle's theorem is a fundamental theorem and has given all the proofs of mean value theorem. So this is a constant term which if you put it over here, which eventually would become FNC at n factorial. A would become that. Let us see how do we go about it. So if we consider this function g of t, are we making it sure that g of t obeys the prerequisites of Rolle's theorem? Let us cross check. What will be g of and what will be g of x? Here the variable is t. So g of x is going to be equal to f of x. Can you see that? G of x, because x minus x is going to be 0 every time. So it is easy. So g of x, note, g of x is equal to f of x. Correct? And what is g of a? What is g of a? G of a. That means you are supposed to substitute a in the place of t. Is this, are we getting this equation with only a here? Because that is what we are supposed to prove. So if I put t is equal to a, then some remainder term looking like this is going to be there, and we will get this quantity after we complete our proof. What should be the quantity, what should be the value of a? That is what is the proof of this theorem. It should look like this. So if you put t is equal to a, do you see that it is also equal to f of x? So to the extreme 2 points, if you consider the function g, then it has got same values. That is the first requirement of Rolle's theorem. Second requirement of Rolle's theorem was the function should be continuous. I mean, f should be continuous over closed interval a comma b, and f should be differentiable over open interval a comma b. Okay, so now two conditions are also given over here: n minus 1 continuous and nth function is differentiable over it. So for all practical purposes, this g of t, which is being defined right now, is eligible to apply Rolle's theorem, and therefore applying Rolle's theorem to g of t, get the value of capital A. That will complete your story of this particular theorem. Applying Rolle's theorem, you get the value of capital A, which we have defined here in terms of g of t in terms of A. If you get this A, we will be able to say that this theorem is done, because you are supposed to get value of A eventually fn c upon n factorial. Okay, so everything is told to you. Now you are supposed to use Rolle's theorem, apply Rolle's theorem. Now applying Rolle's theorem means you are supposed to differentiate g of t. Note the variable here is t and not the x. So you are supposed to find g dash of t, and is to be evaluated at c equated to 0. You will get value of capital A. That is the pending work as far as this theorem is concerned. This is Taylor's remainder theorem. So the proof is differentiate g of t and evaluate it c equated to 0. You find out this A, and as I earlier said, this capital A is expected to be nth derivative evaluated at c upon n factor. That is Taylor's remainder. This is Taylor's remainder. Okay, so I will actually perform the differentiation tomorrow's lecture, next lecture, and we will arrive at A, and then we see whether this remainder term will help us to sort out which particular series expansions are valid and which are not. That we discuss in the next lecture.